Hello, my name is Anna Maria Minda, and today I will talk about the classification algorithm for prostate cancer lesions using three-dimensional MRI scans. Prostate cancer represents the second most diagnosed cancer type in men. The diagnosis procedures are time and resource consuming and directly dependent on the radiologist's experience. It is done through biopsy, histopathology, PSA, and DRE measurement. The MRI scans represent an improvement in the diagnosis procedures. The clinically significant prostate cancer is more easily detected, and the number of biopsy procedures is reduced. The screening is done through DRE and PSA estimations, as well as through TRUS biopsies. An experienced radiologist can manually examine a prostate MRI scan in about 30 to 45 minutes. Through computer-aided diagnosis systems, the examination is done automatically. This allows the doctor to spend more time in treating the patient instead of diagnosing the disease. The source code of the algorithm is public and posted on GitHub. The repository contains Jupyter notebooks with instructions on how to run the modules, on how to visualize the data, and on how to train and test the algorithm. The proposed solution is a classification algorithm that analyzes a data set of three-dimensional MRI scans and classifies the prostate cancer lesions as malignant or benign. The dataset used in the development of the algorithm is the training dataset offered by the Prostate X Grand Challenge. The dataset contains 330 prostate cancer lesions from 204 patients. 76 of the lesions are malignant, and 254 of the lesions are benign. The lesions are compressed in 204 DICOM files. Each file represents the medical data from one patient in the dataset. A three-dimensional MRI is composed of three planes of sequences from which slices can be extracted: the sagittal plane, the coronal plane, and the transverse plane. For this algorithm, only the transverse sequences were used. The dataset provided by the Prostate X Grand Challenge contained 4 types of medical images. T2-weighted sequences. It is a basic pulse MRI sequence. It highlights differences on the T2 relaxation time of tissue. ADC sequences. It stands for apparent diffusion coefficient. This is a measure of the magnitude of diffusion of water molecules within tissue. K-trans sequences. It is a measure of capillary permeability obtained using dynamic contrast enhanced magnetic resonance perfusion. And DWI sequences. It stands for diffusion weighted imaging. These sequences are based upon measuring the random Brownian motion of water molecules within a voxel of tissue. Notice the fact that there are 3 types of contrast in a DWI sequence. They are called p-values, and they measure the degree of diffusion weighting applied. There are 3 main parts involved in the development process of the classification algorithm: data preparation, data visualization, and the model's training and evaluation. The data preparation module involves a few steps: conversions of the sequences in the NIFTI format, sequences sorting, DWI sequences decompression, gathering the information in a data frame object, and storing the information in a pickle file. The DWI sequences compress 3 p-values and are fed to the algorithm as 3 separate files for each patient. The purpose of data visualization module is to get a better understanding of the dataset images. Through this module, multiple steps for the data preparation were discovered. The decompression of the DWI sequences, the filtering of the sequences based on the plane, and a decision to feed the algorithm only with transverse sequences. The last module is focused strictly on the algorithm. It involves the dataset split in 3 subsets: the training, validation, and testing subset. It involves the creation of transform and data load objects for each subset. And it involves the training, the validation, and the testing process. The classification algorithm was developed using the PyTorch and Monash frameworks. PyTorch is a framework based on the Torch library, and it is used in computer vision applications. The 3 main advantages of using PyTorch are its ability to compute tensors through GPU, its deep neural networks, and the easy usage of the GPU unit. Monash is a framework based on PyTorch, and its focus is to make deep learning available in medical imaging. It was officially launched in 2020 through a collaboration between NVIDIA and King's College London. The solution's architecture is quite simple. The MRI scans provided by the Prostate X Grand Challenge dataset are decompressed and converted in the required format, which is the NIFDI format. This is done on the local workstation. Then the dataset is processed through a 3-dimensional DenseNet 121 classification network. The parameters resulted from the training process are stored in a model that is later used in the evaluation stage. The algorithm is based on a 3-dimensional DenseNet 121 network. The name means densely connected convolutional network. Based on the Monash documentation, the 3-dimensional networks are not pre-trained. A DenseNet 121 contains 1 layer of 7 by 7 convolutions, 58 layers of 3 by 3 convolutions, 61 layers of 1 by 1 convolution, 4 average pooling layers, and 1 fully connected layer. The name of the network implies that each layer is directly connected to the next one. It means that for n layers, there will be n plus 1 times n divided by 2 direct connections. The advantages of using a DenseNet are that these networks strengthen feature propagation, encourage feature reuse, and substantially reduce the number of parameters. For the algorithm's training and evaluation processes, the dataset was split based on the number of patients. The split ratio is 0.8, which means that 80% out of 204 patients were used for training and validation, and 20% were used for testing. This resulted in 163 patients and their medical data to be used for training, 33 patients and their medical data to be used for validation, and 41 patients and their medical data to be used for testing. The medical data for each patient contained T2-weighted sequences, ADC sequences, 3 p-value sequences from the DWI sequences, K-trans sequences, and the Lesions labels. The selection of the algorithm's properties was experimental in the training process. The best properties based on multiple training trials and tunings were 50 epochs, binary cross entropy as a loss function, and an ADAM optimizer with a learning rate of 10 to the negative 4 power. The model was trained, and the best parameters resulted from the validation process were stored in a PTH file. The resulting model was used in the testing process, and the following KPI metrics were calculated: accuracy, precision, recall, and F1 score. The algorithm's rate of success is over 80% in the validation process and over 70% in the testing process. However, there are a few interesting numbers that resulted in the evaluation process, like 0 and -1. These values were used to mark some special cases. Either the recall value was 0, which meant that the model didn't classify any malignant lesion correctly, or the model classified all lesions as benign, and the precision value was marked with a negative number to avoid a division by 0. Both these cases led to the marking of F1 score with 0 because calculating its harmonic average between precision and recall would have been irrelevant. These special cases appeared due to factors such as lesion class imbalance or the random selection of the patients. The dataset is small, which means that the chances of a class imbalance are even higher when splitting the dataset randomly. In conclusion, the proposed algorithm is focused on classifying the prostate cancer lesions in three-dimensional MRI scans. The scans and the labels were analyzed and pre-processed, which led to creating a unique architecture based on frameworks such as PyTorch and Monash. As further steps, the architecture should include more deep learning networks, such as lesion detection and segmentation. This would simplify and improve the diagnosis process. However, it is important to remember that a computer-aided diagnosis represents just the first medical opinion. The output of the algorithm must always be double-checked and confirmed by an experienced radiologist. Thank you for watching.